So today we are going to see the rolling motion and rotational equilibrium of body. Okay, so let's discuss rolling motion. So now what is rolling motion? So suppose this is a body which is moving with velocity v, and this is purely translational motion. Translational means it is moving in a straight line, okay, like this. So all particles of this body will have velocity equal to v. Let's say velocity of all particles is equal to v. Then now consider this body. Okay, suppose this is a spherical body, so it is rotating. Okay, it is rotating purely. So now what is rolling? So rolling is addition of translational and rotational motion. Okay, so rolling motion, you can say it is sum of the translational and rotational motion. So if you see this rotational motion here, now we know that velocity of, suppose angular velocity of this body is equal to omega, then velocity of points at end, okay, velocity at distance r will be equal to what? R times omega. We know that v is equal to r times omega. See, so here r is equal to capital R, okay, radius is capital R, so v is equal to r times omega, right? So now if rolling motion is combination of these two, translational motion and rotational motion, that means now if body is rolling, okay, if body is rolling and its center of mass, which is the center, it is moving with velocity v, right? Then what will be velocities of different points? So it will be just sum of velocities in translational motion and velocities in rotational motion, right? Okay, it is just sum of velocity of translational motion and velocity of rotational motion, because rolling motion is combination of translational and rotational motion. So velocity of this point, okay, velocity of this point would be equal to v, translational velocity, plus omega times r, okay, this tangential velocity at this point, okay, so it is equal to v plus omega r. Then velocity of this point, if you see, its linear velocity was v and rotational velocity at this point is suppose omega r, then it is v minus omega r, because linear velocity and rotational velocity, they are in opposite direction, right? And then we have studied this thing that center of mass is the only point which purely rotates, right? It doesn't perform circular motion. So this point won't have any velocity, okay, all in case of rotational motion, okay, this point will not have any velocity. So all points, they just revolve around the center of mass, okay. So then what would be velocity of this point? So velocity of this point would be equal to what? Velocity in translational motion, that is v, and velocity in rotational motion is 0. So velocity of center of mass is equal to v, okay. So then if you consider this point, then its linear velocity is directed like this, its rotational velocity is directed like this. So what would be its velocity? It will be vector sum of these two, okay. So this thing is clear, everyone. So then now a body is purely rolling without slipping, okay, body is not at all slipping on this surface, right? So then there is no sliding at all, then v must be equal to omega r. This is the condition, okay, v is equal to omega r. So velocity of linear motion and velocity of rotational motion, it should be equal, right? So then velocity of center of mass would be just equal to omega times r. What about this point b? B is the point of contact between this body, okay, between this wheel, you can say, and the floor. B is the point of contact. So the velocity of this point would be equal to 0, okay. So this point doesn't slide at all. This point of body, it doesn't slide at all, it doesn't move. What happens is this next part, you can say, these points, they fall down, and therefore what happens, new point of contact will be made between the body and the surface. This point will be lifted up, okay. This thing is clear. So velocity of this point would be equal to 0. So its linear velocity is v, okay, or you can say translational velocity is v and rotational velocity is minus omega r. If v is equal to omega r, then velocity of this point would be equal to 0, right? Then velocity of center of mass, as we said, it is equal to omega times r. What would be velocity of this point at the top? It would be just equal to omega r plus omega r, that means 2 times omega r. So if you see from this point upwards, velocity of this point is 0, velocity of this point is equal to omega r, velocity of this point would be omega r plus omega r, that means 2 times omega r, right? These are the velocity of these different points, okay? Point at the bottom, then center of mass or center, and the point at the top, okay? Then what about this point and this point? So these are the midpoints, you can say. So v is equal to omega r, then if v is equal to omega r, then the vector sum of this thing will be, by parallelogram law of vectors addition, it will be directed like this, okay? Velocity of this point will be directed like this, and what would be the vector sum? Vector sum would be equal to just root 2 times of omega r, right? It will be root 2 times of omega r. So this thing is clear. Is this thing clear? Okay, good. So there can be a direct question based upon this topic, right? So then let's talk about the kinetic energy in case of rolling motion. So we have just studied that rolling motion is just combination of translational motion and rotational motion. So the kinetic energy in the rolling motion, it would be just sum of the kinetic energy of translational motion and kinetic energy of rotational motion, right? So kinetic energy in translational motion is half of mv square. Suppose this body is moving with speed v, so it is half of mv square. And kinetic energy of rotational motion is what? It is half of I times omega square. I is moment of inertia of this body, right? So then we know that moment of inertia in terms of radius of gyration is equal to mk square, okay? Moment of inertia in terms of radius of gyration is given by I equals to mk square. So then just put that over here. What do we get? Kinetic energy of rolling motion of this body, it is equal to half of mv square plus half of mk square omega square, okay? And then you can take m common, right? And you can put omega is equal to v by r, or v is equal to r times omega, or omega is equal to v by r. If you substitute that, omega is equal to v by r. So what do you get? So in this term you will get mk square times omega is v by r, so you will have v square by r square in place of omega square. Then what you can do is you can take half of mv square common from these two terms, okay? And then what you are left with is kinetic energy of rolling motion. It is equal to half of mv square multiplied by 1 plus k square divided by r square, okay? Half of mv square multiplied by 1 plus k square divided by r square. This is the kinetic energy of rolling motion. So we need to remember this formula, okay? It's very simple formula. Half mv square 1 multiplied by 1 plus k square by r square, okay? And then this is in terms of kinetic energy of linear motion. If you want it in terms of kinetic energy of rotational motion, what you can do is you can substitute v is equal to r times omega, okay? So just substitute v equals to r times omega over here. So what do you get? So it is half of m r square omega square, okay, plus half of mk square. And then once again what you can do is you can take you can multiply and divide this term by k square, okay? You can multiply this thing and divide this thing by k square. So then what you can do after that, so you can take half mk square common, so that is your I. You can take omega square common. So again what you are left with is half I omega square multiplied by r square by k square plus 1, okay? Half of I omega square r square by k square plus 1, right? So this thing is clear. Yes, no? Okay, so this formula we need to remember, and whenever we want we can just substitute V is equal to R omega to get that formula. Okay, V is equal to R omega. If we substitute over here, we can get this formula, right? Okay, so then let's talk about the rolling motion of a body on an inclined plane. So suppose this body is just rolling on this inclined plane. Okay, so now this body will have some potential energy at the top. Okay, at this point the body will have some potential energy, and as it rolls down, this potential energy will get converted to the kinetic energy. Okay, so I can say the potential energy at top is mgh. It's equal to kinetic energy at the bottom, which is equal to, we have just studied kinetic energy in rotational rolling motion. It is equal to half of mv square multiplied by 1 plus k square divided by r square. Okay, kinetic energy in rolling motion is half mv square 1 plus k square by r square. So equate that kinetic energy with potential energy at the top. So what do we get? Then we can cancel out m and m. Again we can move 2 on that side. Okay, 1 plus k square by r square on that side, right? And then we'll get v square. If we take square root of that, we get v is equal to square root of 2gh divided by 1 plus k square by r square. Okay, this thing is clear. Velocity at the bottom would be equal to square root of 2gh divided by 1 plus k square by r square. Is this thing clear, everyone? Right. Okay, then let's see next point. So now next I want to find out acceleration for this rolling motion. Okay, so what is the acceleration of this body? So we know that acceleration in case of linear motion is what? It is g sine theta. Okay, if this plane is inclined at an angle of theta, and if this is a smooth plane, then the body will accelerate. Okay, body, if it slides down the inclined plane, then its acceleration is equal to what? G sine theta, if it is a smooth plane, right? So now we want to find out what would be the acceleration in case of rolling motion. Okay, so once again what we can say is v square at the bottom is equal to u square plus 2as. We can make use of the kinematic equation of motion, right? And then we can use this formula for v. V is root of 2gh divided by 1 plus k square by r square. So we want v square, so that will be just square of this thing. So 2gh divided by 1 plus k square upon r square. 2gh divided by 1 plus k square by r square. And suppose body was released with 0 velocity, so we can get rid of this u square because u is equal to 0. Okay, so u is equal to 0, right? Then acceleration is a. Okay, so we have 2 times a multiplied by s, and if you see in this diagram, we have sine theta is equal to h upon s. So what is s? Move s on this side, sine theta on other side, so we get s is equal to h divided by sine theta. Okay, so what is s? S is equal to h divided by sine theta. Then we can cancel out h and h. Okay, move sine theta on that side, so what do we get? We get a is equal to g sine theta divided by 1 plus k square upon r square. Okay, this thing is clear. Is this formula clear? G sine theta divided by 1 plus k square upon r square. Right? Okay, good. And then the next one. Now suppose I want to find out the time taken by this body to roll down an inclined plane. Okay, time taken by a spherical body, or suppose a disc shaped wheel or a ring, to roll down an inclined plane. So for that we make use of another kinematic equation. So s is equal to ut plus half of at square. So u is 0, that means s is equal to half of at square, and you just found a is equal to g sine theta divided by 1 plus k square by r square. Just put it over there. So we get t is equal to, okay, we'll get t square equals to, take this thing on other side. So it will be 2 times s multiplied by 1 plus k square by r square divided by g sine theta, right? So t is equal to root of, therefore t would be equal to square root of 2s multiplied by 1 plus k square by r square divided by g sine theta. Okay, and you can write this as, okay, t is equal to square root of 2s divided by acceleration in the rolling motion. Okay, acceleration of a body rolling down an inclined plane. Okay, it is g sine theta divided by this term 1 plus k square upon r square. What is t? T is equal to square root of 2s divided by acceleration in rolling motion. Okay, this is clear? Yes, no? Okay, good. So now if you look at this formulae carefully, then see, now if a body is sliding down an inclined plane, what is its velocity? Velocity of sliding down, it is just square root of 2gh, right? It is just square root of 2gh, the velocity at the bottom. Okay, so velocity in case of rolling motion is this velocity in case of sliding motion divided by this factor. Okay, so which you can call it as rolling factor. Okay, divided by f. F is the rolling factor. So what is that? It is 1 plus k square by r square. Okay, it is just 1 plus k square by r square. So you can say velocity of the body at the bottom in case of rolling motion, it's equal to velocity in case of sliding motion divided by root of f. Okay, divided by root of f. So what is f? 1 plus k square by r square. You can say this is a rolling factor, right? Then acceleration in sliding motion on a frictionless surface. So we know this, if body slides down on a frictionless surface, then its acceleration is given by g sine theta, right? If body slides down on a smooth surface, its acceleration is given by g sine theta. So if body rolls down on an inclined surface, okay, smooth inclined surface, then this is in case of rolling motion. Okay, the earlier one was in case of sliding motion. So this is for the rolling motion on a frictionless surface. So rolling motion, let's say, not frictionless surface, body rolls down on a surface, then acceleration in case of this rolling motion would be just g sine theta divided by the rolling factor. Okay, acceleration in case of the rolling motion is g sine theta divided by rolling factor f, which is 1 plus k square by r square, right? So you can just say that it is acceleration in case of sliding motion divided by f. Okay, is this thing clear, everyone? Okay, good. And then time taken by body to slide down on an inclined surface in case of sliding motion is just t is equal to square root of 2s divided by acceleration in sliding motion, which is equal to g sine theta, right? Acceleration in sliding motion is g sine theta. So time taken is just square root of 2s divided by g sine theta. Then what is the time taken by body to slide down in rolling motion? Not slide down, roll down. Time taken by body to roll down on an inclined surface. So that is equal to square root of 2s divided by acceleration in rolling motion. Okay, square root of 2s divided by acceleration in rolling motion, which is g sine theta divided by f, and that f you can move to the numerator. What is f? F is equal to 1 plus k square upon r square. Okay, so is this thing clear to everyone? So now let us discuss some simple questions based upon these things, that is rolling motion So a solid sphere, a disk and solid cylinder, all of same mass and radius are allowed to roll down. Okay, solid sphere, disk and solid cylinder, all of same mass, they are allowed to roll down. Uh, Roll down from rest on an inclined plane. Then solid sphere reaches the bottom first, solid sphere reaches the bottom last, then disk will reach the bottom first, all reach the bottom at the same time. Tell me which one would be the answer. This is an inclined plane, suppose, and they roll down on an inclined plane. Which one would be faster? Okay, so for that you can just take the formula for time taken in case of rolling motion. Okay, it is just 2s divided by what? G sine theta. Okay, that is acceleration in rolling motion. I will write acceleration in rolling motion. And what's acceleration in rolling motion? It is g sine theta divided by 1 plus k square by r square. So that is equal to 2s upon g sine theta, and divided by this is multiplied by its reciprocal, so 1 plus k square upon r square. Okay, so now this factor is same for every body, right? S is same, right? Distance covered in case of in the rolling motion would be equal, then theta is equal, so sine theta is equal, so this thing is same. So the time taken just depends on this thing, root of 1 plus k square by r square. So I can just say time taken is proportional to square root of 1 plus k square by r square. So if k is more, time taken would be more. If k is less, time taken would be less, right? So let's compare the radius of gyration, okay, of a solid sphere. What is the radius of gyration of solid sphere? Tell me, radius of gyration of a sphere is equal to, yes, anyone? Okay, that is moment of inertia 2 by 5 mr square. So radius of gyration is just 2 by 5 square root of 2 by 5 multiplied by r. Sorry, this is k for solid sphere, radius of gyration of solid sphere. Okay, so I denoted by r, let's denote it by k. Then what about the disk and solid cylinder? For disk and solid cylinder, k for disk as well as solid cylinder, okay, it is same, it is r by root 2, right? So which one is greater? This one is greater or this one is greater? That means 2 by 5 is greater, or 1 by 2 is greater? 1 by 2 is 0.5, and what is 2 by 5? It's 0.4, right? So this is 0.4, square root of 0.4, and this thing will be square root of what? 0.5. So obviously this thing is greater. Okay, so the disk and cylinder, they will take more time compared to that of sphere. Which will roll down fastest? Solid sphere reaches the bottom first. It is option A, right? Is it clear, everyone? All right, so simple problem if we know the formula, okay, and also if we know the radius of gyration, right? Let's see next one. A solid homogeneous sphere of mass m and radius is something, let's say r, is moving on rough horizontal surface, partly rolling and partly sliding. During this kind of motion of sphere, what will happen? Total kinetic energy is conserved. Angular momentum of sphere about the point of contact with the plane is conserved. Only it is moving on rough horizontal surface. Okay, it's not an inclined surface, rough horizontal surface. So the angular momentum of sphere about the point of contact with the plane is conserved. Next is only rotational kinetic energy about the center of mass is conserved. Then angular momentum about the center of mass is conserved. Tell me. Okay, let me explain this one. So now if it is sliding, it is rough surface, so its total kinetic energy cannot be conserved, right? Because it's sliding, so there is some friction, kinetic energy will decrease. Kinetic energy decreases, then there is relation between linear and rotational motion also. Okay, so therefore since kinetic energy is decreasing, its whole kinetic energy will decrease, so rotational kinetic energy will also decrease, and that's why only rotational kinetic energy about the center of mass is conserved. This is also not correct. So then you need to check the remaining two, that is angular momentum about the center of mass is conserved, this point, and the angular momentum of a sphere about point of contact with the plane is conserved. Okay, so let's check these two. So now if you take a solid sphere, so this is a solid sphere, okay, so when would be the angular momentum conserved? So if torque is equal to 0, angular momentum is conserved, L remains constant, right? So now 2 points are given. Which are those 2 points? The first one is the point of contact, okay, between the sphere and this surface. Second one is the center of mass, right? Second one is center of mass. So now this is center of mass, okay, this is center of mass. So now you think of the forces that are acting, okay, what are the forces acting on this one? So one is the frictional force, okay, so one is the frictional force. In what direction is it acting? So if this body rolls like this, okay, rolls like this and slides in forward direction, that means friction would be acting in backwards direction, right? Friction acts in backwards direction. What else? Then there would be gravitational force acting on it, okay, that is mg. What else? There would be a normal reaction, right? There would be a normal reaction which acts upwards. So this is the normal reaction, acts upwards, right? So these are the three forces. Now see, what would be torque due to these forces about the center of mass? So you can see that normal reaction and gravitational force, they are passing through the center of mass. If you take its direction, okay, so it is along this line. This line passes through the center of mass, right? This line passes through the center of mass. So that's why the perpendicular distance of n, okay, perpendicular distance of n and mg about center of mass, okay, or you can say from the center of mass, is equal to 0, and therefore there is no torque due to the normal reaction and mg, right, about the center of mass, and therefore torque about cm, torque of which forces? Torque due to n and mg about cm about center of mass would be equal to 0. Okay, but then you see the frictional force. So frictional force is at a perpendicular distance of r from the center of mass, but torque due to frictional force, torque due to frictional force, torque due to, let's say, F, okay, about the center of mass, about center of mass, it is not 0, so it is just equal to r multiplied by F, rf sine theta, but the angle would be equal to 90 degrees, right? So this is not equal to 0. Okay, so if torque is not 0, then will the angular momentum uh, will be the angular momentum conserved? Will the angular momentum be conserved? No. So the angular momentum about center of mass is not conserved. So this is also incorrect, right? That means it is option B. Okay, option B, no? Angular momentum of sphere about the point of contact. Yes, it is option B. So now how? So see, all of these forces, they pass through the point of contact. So therefore perpendicular distance of these forces about the point of contact is 0. So there is no torque exerted by any of this force, okay, about the point of contact, and that's why angular momentum of sphere about the point of contact with the plane is conserved, right? Is this point clear to everyone? Okay, why, which one is wrong? Option C. You said option C, no, Yamini? Option A and C. Okay, so since, see, what's happening, it is slipping on a rough surface. So if it is slipping on a rough surface, what will happen? Kinetic energy cannot be conserved because there will be loss of energy. It is slipping, no? So there is some work done against the friction, right? So some energy is lost. That energy will get converted to heat. So kinetic energy cannot be conserved. Okay, so that's why A and C are not correct. Right, good. So then let's see next one. See, this is very old question but good question. Let's see next one. The speed of a homogeneous solid sphere after rolling down an inclined plane of a vertical height h from rest without sliding is. So speed of which thing? Solid sphere. So this is just formula based question. It is rolling down on an inclined plane, okay, from height h. We have the formula. Velocity of rolling is square root of 2gh divided by rolling factor, and what's that? 1 plus k square upon r square. And what is it? So write the formula first, then see what is it. So it's solid sphere. Solid sphere means k is equal to root 2 by 5 r. That means k square is 2 by 5 r square. Okay. So k square by r square is equal to what? 2 by 5. So just substitute that here. Okay, substitute that here. So what do we get? We get it is root 2 gh divided by 1 plus 2 by 5 means this is 7 by 5. That 5 goes to the numerator. 5 times 2 is 10. Right. So it is square root of 10 gh divided by 7. Okay. So this is my g. Right. So it is option A. So this one is clear. Very, very simple, right? Yes, Indusha, good. Nikita, okay, good. Let's see next one. A solid spherical ball rolls on a table. The ratio of its rotational kinetic energy to total kinetic energy is. Okay. So now this thing I will explain here, but okay, rotational kinetic energy. What is that? Solid spherical ball, right? What is rotational kinetic energy? Let's say Ke rotational divided by, we want total kinetic energy. So that is Ke rotational plus Ke translational. Okay. So see, Ke rotational will be half of I into omega square. Okay. Divided by, you have half of rotational is half of I omega square, and what is translational kinetic energy? So you can say it is half of mv square. Okay, right? Or you could write this thing as half of m k square omega square. Sorry, half of v is equal to r into omega, half of m into r square omega square. So omega square will get cancelled out. So then what I will do is I will substitute I equals to what? Mk square. Okay, mk square. So put that. So you have half cancelled. I is equal to mk square. You have mk square omega square. This I is equal to mk square. Okay, you have mk square omega square. And what is this v? V is r omega. So you have m multiplied by r square omega square. Okay, so m gets cancelled out, omega square gets cancelled out. So what do you get is finally k square divided by k square plus r square. So this is rotational kinetic energy divided by total kinetic energy is this thing. Okay, now put the value. So it is a solid spherical ball. So once again, solid sphere. So you have k equals to what? K equals to square root of 2 by 5. Root 2 by 5 r, right? So take square of that. So k square is equal to 2 by 5 r square. Okay, you can put that everywhere. So this is equal to 2 by 5 divided by 2 by 5 plus 1, right? What I am doing is this is 2 by 5 r square. In denominator you have once again 2 by 5 r square plus r square. You can cancel out r square everywhere. So this is 2 by 5 divided by 2 by 5 plus 1, right? So you can cancel out 5 everywhere. So this thing will be 7 by 5. Okay, this thing will be 2 by 5, 5 cancelled. So it is 2 by 7. So the answer is 2 by 7. Okay, so here we solved it, but then now you will remember this formula. That the ratio of rotational kinetic energy to total kinetic energy in rolling motion. Okay, so in rolling motion, rotational kinetic energy divided by total kinetic energy, it is equal to k square divided by k square plus r square. Okay, so we just found this k square divided by k square plus r square. And also similarly we can find out the translational kinetic energy. Okay, translational kinetic energy divided by total kinetic energy is r square divided by k square plus r square. Okay, so just remember this formula. Rotational Ke by total kinetic energy is k square divided by k square plus r square, and translational kinetic energy divided by total kinetic energy is r square divided by k square plus r square. Okay, so this thing is clear. Right, good. So remember this formula. Then formulas. Then let's see next one. A disk is rolling. The velocity of its center of mass is VCM. Which one will be correct? The velocity of highest point is 2 times velocity of center of mass, and at the point of contact it is 0. The velocity of highest point is VCM, and at the point of contact is VCM. Okay, the velocity of highest point is 2 VCM, and at the point of contact it is VCM, and the velocity of highest point is 2 VCM, and at the point of contact it is 2 VCM. Which one is correct? We have seen this thing. a disk is rolling, then velocity of this topmost point is equal to what? So this is the center of mass. Its velocity is equal to velocity of center of mass, right? Velocity of this topmost point, it is 2 times velocity of center of mass, and the point of contact is at rest. Okay, so this was the first point that we studied, right? Okay, so which option is correct? It is option A, right? The velocity of highest point is 2 VCM, and at the point of contact it is 0, right? This is clear? Okay, good. Very simple question. Let's see next one. A solid sphere of radius r is placed on a smooth horizontal surface. A solid sphere of radius r, it is placed on a smooth horizontal surface. A horizontal force F is applied at height h from the lowest point for maximum acceleration of center of mass. Which is correct? Okay, tell me. So you exert a horizontal force like this, okay? The force is F, and the question is, for the maximum acceleration of center of mass, which of these is correct? This is the question. Tell me. Okay, so when we studied about the center of mass, we studied that external force is just equal to mass of the body multiplied by acceleration of center of mass, right? Suppose you are exerting some force F on the body, it is equal to mass of body multiplied by acceleration of center of mass. Now, does this formula depend at which point you are exerting that force? Okay, does this point depend on the point at which the force is exerted? Yes, no? No, it does not depend, right? Good. So center of mass, the acceleration of center of mass is independent of where you apply the force on the body. Okay, so you exert force on body, that force is suppose F, then acceleration of center of mass is F divided by mass of the body. That's it, right? So there is no relation between H and R. Okay, this one is correct. Is this thing clear? Okay, let's see next one. Consider a contact point P of a wheel on ground which rolls on ground without slipping, right? Consider a contact point P on ground which rolls on ground without slipping. Then the value of displacement of point P when the wheel completes half rotation if radius of the wheel is 1 meter. Okay, what would be displacement of this point P which is in contact with this floor? So question is, what would be the displacement of this point P when the wheel completes half rotation? When the wheel completes half rotation, where will this point go? it completes half rotation? No. So that means this point will go at the top, right? The point will go at the top. It's option B. Okay, let's check. So then, how much is this distance? So for full rotation, if it completes full rotation while rolling, then the point will come back over here. So the distance covered would be equal to what? Point starts from here, okay? And that means that point of the body or the wheel, it makes contact with the floor. And once again, it will make contact with the floor. So distance covered would be equal to 2 pi r. But here, it is half rotation only. So distance covered is just equal to pi r. Okay, so distance covered is pi r. Then question is, what is the displacement of this point? What is the displacement of this point? Right? So just join the start point and end point and then find out the displacement. This is the displacement, right? S is the displacement. So it is just, what is this distance? This is 2r, right? This is 2r. Okay. So you can say S is equal to, using Pythagoras theorem, square root of pi r square plus 2r square, and r is equal to 1. Okay, that means it is pi square plus 4, right? Very good, Yamini. So pi square plus 4. Okay, so it is option B. Okay, this is simple, right? Okay, good. Then let's see next question. A solid cylinder of mass m and radius r rolls without slipping down an inclined plane of length L and height h. So length is L, height h. Then what is the speed of its center of mass when the cylinder reaches the bottom? When the cylinder reaches its bottom. Okay, tell me. Solid cylinder rolls without slipping. Okay, so what would be the velocity of center of mass? It is cylinder, no? Just write down the formula. Velocity of cylinder is just equal to square root of 2gh divided by 1 plus k square by r square. Okay, root 2gh divided by 1 plus k square by r square, rolling factor. So for a cylinder, k for cylinder is equal to r divided by root 2, right? So what is k square upon r square? Therefore k square by r square is just equal to 1 by 2. You put that here, it is 1 by 2, right? 1 by 2 means this thing will be 1 plus 1 by 2 is 3 by 2. So take that 2 in the numerator. So it becomes 2 times 2 means 4, 4 by 3. So this is the answer, right? 4 by 3 GH is the answer. It's option C. Okay, direct formula. Right, everyone? Okay, good. Let's see next one. A ball rolls without slipping. The radius of gyration of the ball about an axis passing through its center of mass is k. Radius of gyration is given. If the radius of ball is r, then the fraction of total energy associated with its rotational energy will be. Okay, so now you have total energy divided by rotational energy. So it's opposite to what we saw earlier. Okay. Then the fraction of Fraction of total energy associated with rotational energy. So it is, okay, how much of total energy is associated with the rotational energy. It's the same thing, right? It's the same thing. So it's option C, k square divided by k square plus r square, right? Okay, good. So this one is repeated. Let's see next one. A drum of radius r and mass m rolls down without slipping along the inclined plane of angle theta. The frictional force dissipates energy as heat. Okay, it rolls an inclined plane without slipping, decreases the rotational motion, decreases the rotational and translational motion, converts translational energy to rotational energy. Okay, a drum of radius r and mass m rolls down without slipping, okay, on an inclined plane. So what does the frictional force do here? Yes, anyone? Okay, is it sliding? See, is it sliding? Is it slipping? Is this drum slipping? No. That means there is no work done. Okay, no sliding means no work against friction. Okay, against friction. And if there is no work done against the friction, that means there will be no energy lost. Okay, so dissipates energy as heat, not correct. Decreases the rotational motion, again not correct because no energy is lost. Okay, decreases the rotational and translational motion, not correct because no energy is lost. Okay, so now that's why it is option D. Okay, right, but let's check option D also. So it converts translational energy to rotational energy. How is it so? So see what happens is, so it rolls down without slipping and there is some friction. Okay, so question is, what does the frictional force do? Means there is some friction. So see, frictional force will act in this direction. Okay, so if there was no friction, then this drum, it would have slide down, right? It would have slide down. Okay, now since there is friction, okay, which opposes the sliding motion, now therefore you can think of friction is just sufficient to hold it over there. Suppose, okay, it doesn't slide down. Suppose it doesn't slide down. So then now what happens is, there is gravitational force, okay, and you can think of it acting down from the center of mass, right? There is gravitational force and you can say that it acts downwards from the center of mass, right? So gravitational force acts like this, in this direction. Okay, and because of this gravitational force, now there would be some torque, right? There would be some torque which causes its rotational motion. Okay, how much is the torque? So just draw R. So torque is equal to R multiplied by mg sine theta, and theta is this angle, right? R is this much from here to here, this much distance is R. Okay, so R bar is directed like this, mg is directed like this, so this angle is theta. So there is some torque due to the gravitational force. Tau is equal to mg multiplied by r sine theta, and because of this thing, what happens, it rolls down. Okay, do r cross f, and you can see that it will roll in this anti-clockwise sense. Is this thing clear? Okay, so that means it converts the translational energy, actually it should be the potential energy, to the rotational energy, right? It converts the potential energy at this point to the rotational energy. Okay, clear to everyone? Okay, good. Then let's see next question. A solid cylinder and a hollow cylinder, both of the same mass and same external diameter, are released from the same height at the same time. Okay, too much of same. A solid cylinder and hollow cylinder, both of same mass same. Okay, solid and hollow cylinder. Then same external diameter, same diameter, are released from the same height. Okay, good. Then both roll down without slipping. Okay, then which one will reach the bottom first? Okay, which one will reach the bottom first? So we know that T is equal to what? It is square root of 2s divided by acceleration in rolling motion. Okay, and which is equal to square root of 2s divided by g sine theta multiplied by 1 plus k square upon r square. Okay, so this is the formula, right? Okay, it's option D. Let's check. So now k should be smaller. Okay, so time is more if k is more. Okay, time is directly proportional to 1 plus k square, root of 1 plus k square upon r square. So time taken would be more if k is more. So out of these two, solid cylinder, k for solid cylinder and k for hollow cylinder, which one is greater? For solid cylinder it is r by root 2, for hollow cylinder it is just equal to r. So of course for hollow cylinder it is greater, means it is lesser for solid cylinder. So solid cylinder will reach the bottom first. Okay, so option D is the answer. Correct. Right? This is simple. Okay, so this option is nice. Both together only when the angle of inclination is 45 degrees. All right. So option D is answer. Okay, let's see next one. A solid cylinder of mass 3 kg is rolling on a horizontal surface with velocity of 4 meters per second. Okay, solid cylinder means, let's just write down what is K. K is R by root 2. Okay, it collides with a horizontal spring a force constant 200 Newton per meter. The maximum compression produced in the spring will be. So it's a solid cylinder. Let me explain this. You have a solid cylinder like this. Okay, and it rolls down on a horizontal surface. It rolls down on a horizontal surface, this surface. Oh, horizontal surface. Okay, and then after that there is a spring. So it collides with a spring. It collides with the spring, suppose. And then there would be some compression in this spring. So this is the rigid support. Right? So now question is, how much is the compression. So again, it's similar. We have seen problem like this in the collision. Okay, so what happens is the spring will be compressed till the time whole kinetic energy of the cylinder gets converted to the potential energy of the spring, right? So Ke of cylinder gets converted to potential energy of spring, and that means what is kinetic energy of cylinder? It is half mv square multiplied by 1 plus k square by r square. Okay, this is kinetic energy in rolling motion. It's equal to potential energy half of k into x square, right? Half is cancelled, but then this k and that k is different, right? This k is radius of gyration and this k is the force constant. Okay, so I guess there is no confusion. Or let's say this is capital K, okay, and this one is small k, right, lowercase k, or we can say this is kappa. Okay, but we know what's that, right? So half is cancelled. Move this k on other side. So then you have x square is equal to that kappa or k small k multiplied by mv square, okay, multiplied by 1 plus k square by r square. Then put the values. There is nothing, right? So let's put the values. So we have x square is equal to, that's 200 multiplied by, what's the mass, 3 multiplied by v square, that is 4 square. Then you have multiplied by 1 plus k square by r square. So k is,
So the spring constant should come in the denominator.
yeah, correct. Spring constant should come in denominator. Yeah, very good. Yeah, so that should come in denominator. How can I do that? If I appear for NEET, I will do lots of mistakes. Okay, so mv square divided by k. So m is equal to 3 kg, and then you have v square is 4 square divided by spring constant is 200. 200 multiplied by 1 plus k square by r square. So it is r by root 2. Then k is r by root 2. If you take square of that, then you get 1 by 2, right? So this thing will be 3 by 2. Okay, 3 by 2. 1 plus 1 by 2 is 3 by 2. So take square root of that, right? So x is equal to, let's just take square root of this thing. So you have 3 times 3 also here. Okay, this is 3 by 2. So square root of that is 3. Then 4 square root of that is 4. And in denominator, this was 3 by 2, no? So 2 times 2 is 400. Square root of that is 20. So 3 times 4 divided by 20, or you can say it's 3 times 2 divided by 10, means 6 by 10, 0.6. 0.6 meters is the answer. It's option B. Okay, so this is simple, right? Yes, no, very simple question. Okay, let's see next one. A small object of uniform density rolls up a curved surface. Okay, it rolls up a curved surface with initial velocity v. It reaches up to the maximum height of this much. With respect to the initial position, the object is. So once again, this is similar to that of last question. What you can do is, you can say the potential energy at top is equal to kinetic energy at the bottom, right? Because when it rolls up, its kinetic energy gets converted to potential energy. So potential energy at top, PE at top, is equal to KE at bottom. And you want to find out which object it is, so you will need to find out its radius of gyration, right? There is no other way or to identify which object that is, right? So mgh is equal to half of mv square multiplied by 1 plus k square divided by r square. Okay, cancel out mm, then put h is equal to this thing, right? Maximum height of 3v square by 4g. So g multiplied by h is 3v square divided by 4g, that is equal to half of v square times this thing. Okay, so gg gets cancelled, gg gets cancelled. So this is 3 by 4 v square. Okay, so 1 plus k square by r square. Then you can divide this thing by 2. So v square and v square also gets cancelled. 1 plus k square by r square. You get 1 plus k square by r square is equal to, I guess, 3 by 2, right? Because this thing becomes 3 by 2, v square cancelled. Yeah, 3 by 2. So that is equal to 3 by 2. So if that is 3 by 2 means k square by r square is half. Okay, k square by r square is 3 by 2 minus 1, that is half. K square by r square is half, means k is equal to r by root 2. Okay, square root of this is k by r is 1 by root 2. Move r on that side, so k is r by root 2. Then which object that is? Okay, which object it is? Hollow sphere, disk, ring, solid sphere. Which one? Disk. Okay, yeah, good. So it is a disk, right? Very simple. Okay, but this thing should click. That's the point, right? Otherwise, height is given, then which object is that? Okay, so it's not that difficult, right? Okay, let's see next one. The ratio of accelerations for a solid sphere mass m and radius r rolling down and inclined at an angle theta without slipping, and slipping down inclined without rolling. Okay, so this is just acceleration in case of which motion? Acceleration in rolling motion divided by acceleration in sliding motion. That's what you want to find. So what is that? This is g sine theta divided by 1 plus k square upon r square, right? Divided by acceleration in sliding motion is g sine theta. So that g sine theta and g sine theta will get cancelled out. So it is 1 upon 1 plus k square by r square. 1 divided by 1 plus k square. 1 plus k square by r square. So what's that? What is the body? It is solid sphere again. 2 by 5. K square by r square is 2 by 5. Means 1 plus 2 by 5 is 7 by 5. Take that 5 in the numerator. So it will be 5:7. Okay, so answer is 5:7. Right? Because k square by r square is 2 by 5 for a solid sphere. This one is clear. Right? Very simple question. Let's see next one. A disk and a sphere of same radius but different masses roll off on two inclined planes of same altitude, means same height and length. Which one of the two objects gets to the bottom of the plane first? It's a disk and a sphere. Which one will roll down first? I think we have solved this one earlier. It's sphere, no? Okay, so does the speed or does the time taken depend on the mass? It doesn't depend, right? The time taken is just equal to square root of 2s divided by acceleration in rolling motion. which is g sine theta divided by rolling factor, which goes in numerator, 1 plus k square by r square. Okay, so this is repeated, I guess, many times over, right? So t is proportional to 1 plus k square by r square. If k is small, t is less, right? So for a sphere, it is less. That's why answer is sphere. Okay, k for sphere is equal to r root 2 by 5 r, and k for another is disk, right? K for the disk is r by root 2, right? So this one is less. Okay, so that's why answer is sphere. All right, this is simple question, very simple. Of course, if you know the formula, right? Okay, let's see next one. Then this is from NEET 2018. So this is from NTA. A solid sphere is in rolling motion. In rolling motion, a body possesses translational kinetic energy as well as rotational kinetic energy simultaneously. The ratio of kT means translational kinetic energy to that of total kinetic energy. So we have to remember this, right? KT divided by total kinetic energy, kT plus kr. Is what's that? So some time back we wrote down the formula. It is translational divided by total. It's r square divided by r square plus k square. Okay, rotational divided by total is k square divided by r square plus k square. So there is nothing in this problem, right? So what is it's a solid sphere, so k is equal to again root 2 by 5 r. Okay, so that means k square is 2 by 5 r square. So we can just put that. So this is r square divided by what's that? R square plus 2 by 5 r square. So then this thing is 7. 5 goes to the numerator. It's 5 by 7. Okay, make the denominator same here. So this is 1. This is 2 by 5. 1 plus 2 by 5 is 7 by 5. Move 5 in the numerator. So it is 5 is to 7, right? R square will get cancelled out. Okay, so that's very simple. Yes, no. Indusha, Selva Kumar.
Yes, sir.
Okay, good. Let's see next one. A solid cylinder of mass 2 kg and radius 50 centimeter. Okay, good. Solid cylinder of mass 2 kg and radius 50 centimeter rolls up an inclined plane of inclination 30 degrees. The center of mass of cylinder has speed of 4 meters per second. The distance traveled by the cylinder on the inclined surface will be. Okay, what would be the distance traveled? This is the question. Okay, so this is from NEET 2019. And this is also simple, right? So what you can say is you have this formula, or this is solid cylinder, it is rolling up. Okay, so at the top what will happen? Speed will become 0. So you can say that v square is equal to u square plus 2as. It covers distance s, but acceleration will be acceleration of rolling here. Okay, so this is a solid cylinder which rolls up like this, and it reaches, suppose, till this height. Okay, so it covers distance equal to s. S is the distance covered. What would be its acceleration? Will it be positive? Will it be negative? Negative, right? It is rolling up, so acceleration would be negative. Okay, so final velocity is 0, u is given. Okay, so we have v square, that means 0 is equal to u square minus of 2 times acceleration in rolling motion. Okay, that would be negative, so that is g sine theta divided by 1 plus k square upon r square times s, and we want s, so we can move everything else on other side. But first let's move this thing on other side. So we have 2g sine theta times s divided by 1 plus k square upon r square, and that is equal to u square, right? And we want s, so let's move these things on other side. So s is equal to, okay, s is equal to u square times 1 plus k square by r square, that will go in numerator, divided by 2g sine theta. Now put the values. Okay, now let's put the values. So that is equal to, what is u? U is 4 square multiplied by 1 plus k square by r square. So it is solid cylinder. So for solid cylinder, k is equal to solid, no, r divided by root 2. Right, for solid cylinder, k is equal to r divided by root 2. So 1 plus k square by r square would be what? K by r is 1 by root 2. Square of that is 1 by 2. Therefore 1 plus k square by r square is 1 plus 1 by 2, means 3 by 2. Okay, this is 3 by 2 divided by 2g sine theta. So 2 times 10, and it is sine 30. Sine 30 is half, so that thing gets cancelled out. Okay, okay, half and 2 gets cancelled out, and you have 4 square, means 16 divided by 2 is 8 times 3 is 24 divided by 10 is 2.4. Okay, so answer is 2.4 meters. Just some calculation, right? So answer is 2.4 meters. This one is clear? Yes, no? Okay, so see, now you could do this faster. Instead of doing all this, you could just use this formula. It rolls down or it rolls up. So see what happens when it rolls down. Its potential energy gets converted to kinetic energy. When it rolls up, kinetic energy gets converted to potential energy, right? So you already have velocity in case of rolling motion. Okay, it's equal to square root of 2gh divided by 1 plus k square by r square, right? So suppose this is initial velocity now, because it starts with some velocity, rolls and goes to the height h. Okay, and then you have this relation between h and s. What relation? Oh, so this is h, this is s, right? We want to find out s, no? That's why this angle is theta. So sine theta is equal to h by s. Okay, so s is equal to h divided by we want, okay, s. So h is equal to s sine theta. Just substitute that here. Okay, so you have v square is equal to 2 times g into s sine theta, right, divided by this factor 1 plus k square by r square. And then you want s, no? So move everything else on other side, and therefore s is equal to v square times 1 plus k square upon r square divided by this thing 2 times g multiplied by sine theta. Okay, see, you have same formula, u square. So I said make this u. Okay, this is starting velocity, right? So u square or v square, call it anything, but this is the velocity at starting. Okay, multiplied by 1 plus k square by r square divided by 2g sine theta, right? Okay, so you could do this way also, and there is very less chance of error in this one, because see, this formula we derived considering the potential energy at top gets converted to kinetic energy at bottom. Okay, and what's happening in this question, reverse thing is happening. So kinetic energy at bottom gets converted to potential energy at top, right? So the same formula can be used. Okay, is it clear, everyone? Okay, good. Then let's see next one. This is also from NEET 2019. So a disc of radius 2 meters and mass 100 kg rolls up on a horizontal floor. Its center of mass has speed of 20 centimeters per second. How much work is needed to stop it? Okay, how much work is needed to stop it? So work required is equal to the kinetic energy, right? How much work is needed? Whatever energy it has, we want to make that energy equal to 0. So work required to be done is equal to its kinetic energy, right? So that is equal to, what is its kinetic energy? It is rolling, no? It rolls. Okay, so it's half of mv square multiplied by 1 plus k square divided by r square. Just put the values. So it is half of, mass is 100 kg, then v square, v is 20 centimeters per second. So that is 0.2, v is 0.2 meters per second, right? We need to convert this to meters per second. So 0.2 square, okay, multiplied by 1 plus k square by r square. It's a disk. So k is equal to r by root 2. So k by r is 1 by root 2. Therefore k square by r square is 1 by 2. Right, since k by r is 1 by root 2, k square divided by r square is 1 by 2. So then that is half multiplied by 100 multiplied by, this is 0.04 multiplied by 3 by 2. 0.04 times 100 is 4. 4 divided by 2 and 2, that is 1. So 3. So answer is 3. Right, the answer is 3 joules. Option B. This one is clear. So next let's talk about the couple. So what is a couple? Couple means two equal and opposite forces. Okay, two equal and opposite forces acting on a body is a couple, right? So what is the use of this couple? So couple results in purely rotational motion. Okay, for an example, suppose I want to open this bottle. Okay, I want to open this lid. So what do I need to do? I exert a force in this direction. One force is in this direction. The other force is in reverse direction, right? So this is like a couple. Maybe it's equal and opposite. It may not be here in this case, but this is an example, right? Another example is in earlier days, there used to be taps like this. Okay, so this is a tap, right? So have you seen some tap like this? Yes, no? And to open the tap, okay, or to close the tap, again you need to apply two forces like this. Two forces means uh, you make use of two fingers. Okay, one you push like this in this direction, one you push in the other direction. So this is a couple. Okay, so these are some simple examples in our day-to-day life. Is this thing clear? Yes, no? Okay. So then see, this is force F1, this is for force F2 acting on this rod. So now see, these two forces are equal and opposite. So what does that mean? The net force acting on the rod is equal to 0 because there is one force from this side, one force from the other side. Okay. Net force is equal to 0, but net torque is not equal to 0. So there will not be any linear acceleration because there is no net force. There will be only angular acceleration. Okay, so it will only rotate. So let's find out torque due to F1 and F2, both of them. So see, so this F1 is, for simplicity, let's take it at distance L by 2 from this point O. Okay, and suppose axis of rotation passes through the point O. Axis of rotation passes through the point O. Okay, so suppose the rod can rotate about point O. Then what is its position vector? Position vector of F1 is suppose R1. It is directed like this. Can you see this? This is the position vector of F1. Let's call it R1. You can call it anything. Okay. So how much is the magnitude of this position vector? L by 2. And how do we find torque? So it is L by 2, right, multiplied by F1 multiplied by sine theta. Theta is the angle between this R and F. So this is the angle theta. So L by 2 times F1 into sine theta. So this is tau 1. Okay. Similarly, this force F2 is at position vector R2 and its magnitude is also L by 2. Okay. So, right. So how much is this one? So this is also, how much is torque due to this one? So it is also L by 2. So magnitude of position vector multiplied by magnitude of force F2 multiplied by sine theta. Angle between those two is also theta. Okay, if this angle is theta, this angle has to be theta, right? Yes, no? Okay, good. Then after that, now how much would be the total torque? So if the two torques are in same direction, then you will add up the two torques, and if they are in opposite direction, then you will subtract them. So see, the two torques are in same direction. How do you know? Because see, this is position vector R1, you can say it's directed in this direction. Do R cross F. So what will you get? You get direction of torque as outside the plane of the board. You can do that and check. Similarly, this R cross F2 also gives the outside the plane of the board. That means two torques are added up. Okay, is this thing clear? And how will they rotate that body? That body means that rod, this rod. How will it, how will this rod be rotated? In anti-clockwise sense. So you can check that this is R, this is F, R cross F will give anti-clockwise rotation, right? Again, this is R, okay? R is not this much, I am just drawing the direction, right? R is this much only, okay? It is exerted at this point. So this is R, direction of R, this is F. Again, this is also, if you do R cross F, then rotation is in anti-clockwise sense, right? We know torque is equal to R bar cross F bar. Okay. So that means both of them, they are helping each other. So net torque will be equal to tau 1 plus tau 2. Right? Is this thing clear, everyone? Okay. Everyone? Good. So then add up the two torques. So you get L by 2 times F1 sine theta plus L by 2 times F2 sine theta, and the magnitude of F1 and F2 is equal. So F1 is equal to F2 and suppose that is equal to F. So then you have L by 2 times F sine theta plus L by 2 times F sine theta. You can take F sine theta common, and then what is L by 2 plus L by 2? It is L. So the total torque is equal to L multiplied by F into sine theta. Okay. So now see, how can you remember this? So this total torque due to a couple, this is also called as moment of couple. Okay, this is also called as moment of couple because torque is the moment of force. So this is moment of two forces. They form a couple, right? And that's why this is moment of couple. Okay, so moment of couple is magnitude of one of the force, that is F, multiplied by perpendicular distance between two forces. So L sine theta is the perpendicular distance between two forces. See, this much distance is L. Okay, this much distance is L. This angle is theta. See, this angle is theta, so this angle has to be theta. And if you see sine theta, then it's this side, right? This side divided by this side. So it is, you can say AM divided by AB. Okay. So in this diagram, so let me write, for time being I will write it here, that okay. So what is sine theta here? Sine theta is equal to this AN divided by AB. It's equal to AN divided by, not AN, AM divided by AB. Okay. And therefore what is AB? AB is equal to, what is AM? AM is equal to AB sine theta, or you can say L sine theta. AM is equal to L sine theta, right? This much distance is L. And what is this thing? So if you see this force and this force, the perpendicular distance between these two forces is equal to AM, that is equal to L sine theta, right? So our formula is L sine theta multiplied by F, means it is magnitude of one of the force multiplied by the perpendicular distance between two forces, that is the net torque due to a couple. Okay, is this point clear, everyone? Right? Good. So then net force acting on the body is 0. So these are just some points to be noted, and linear velocity of body will remain constant because net force is equal to 0. So couple produces purely rotational motion. Couple produces what? It produces purely rotational motion. So this is simple, right? So now see, for the equilibrium of body, for linear equilibrium, net force acting on the body must be equal to 0. So for the translational means linear equilibrium. So body, if net force acting on the body is equal to 0, then linear acceleration would be equal to 0, right? Okay, so in earlier chapters we studied about this equilibrium only. Now there is condition for rotational equilibrium too, that net torque acting on the body should be equal to 0, then the body will be in rotational equilibrium. Okay, is this point clear? Net torque acting on the body must be equal to 0, then the body will be in rotational equilibrium. Right? If net torque is not equal to 0, then what will happen? So we can say tau is equal to I times alpha, then there will be angular acceleration. Okay, if net force is not equal to 0, there will be linear acceleration. If net torque is not equal to 0, then there will be angular acceleration. Is this point clear, everyone? Okay, good. So for equilibrium, total equilibrium, net force must be equal to 0, total force acting on the body must be equal to 0, and the net torque acting on the body must be equal to 0, right? Okay, after that, let's see center of gravity. Now what is the center of gravity? So it is the point about which the total gravitational torque acting on the body is equal to 0. Okay, so what is that? So suppose this is a body. So now you must have seen this, that in your class there might be some students, they balance the book at, okay, at the tip of one finger, right? You might also do that. Okay, so what are they doing? So see, if you try to balance any book, so for an example, suppose I want to balance this thing, okay, at tip of one finger. Okay, now this is not getting balanced. Why? If weight on this side is greater, weight on this side is greater, it will fall on this side. Weight on this side is greater, it will fall on this side, right? Weight is greater means what? It's not the weight, it is the torque, right? Torque on this side is greater. If there is more mass on this side, the torque due to gravitational force on this side would be greater. So it will get toppled like this. If there is more mass on this side, then torque due to the gravitational force on this side would be greater. So it will get toppled like this. So if you want to balance it, what should happen? Torques should be balanced, right? Okay, so I will not try to balance it. So see, if the body is pivoted about this point, okay, it is suspended, pivoted, one of these two, those two, so about this point, then let's suppose there are n number of small particles within the body, okay, and each particle will have some mass. So now there is some gravitational force acting downwards on each mass, okay, so that force is equal to mg. So then now you have pivoted the body about this point, so there would be some torque due to this gravitational force. So see, this is draw position vector from this point. Suppose this is the origin, draw position vector like this. So position vector, that is your r bar cross f bar. If you do so, see, this is r bar, this is f bar, so r bar cross f bar, so it will rotate the body like this. Okay, okay, so all masses on this side, they will, are not masses, the gravitational force acting on those masses will rotate the body like this. Okay, if masses are on the other side, then the gravitational force on that masses, those masses will rotate the body in opposite sense. Okay, so if you just consider one direction, if you take the masses on one line, then the masses on this side must be balanced to what masses on this side. Okay, right, they must be symmetric about this point. This thing is clear? Yes, no? If you want to hold that body, okay, you don't want it to topple, you don't want it to rotate, then what should happen? So gravitational torque on this side should balance gravitational torque on this side. Yes, no? Okay, and therefore now if you find such a point about which the gravitational torque due to the gravitational force acting on all point masses of the body, if sum of those gravitational torques is equal to 0, then that point is known as the center of gravity of a body. Then that point is known as what? Center of gravity of a body. Okay, and for symmetric bodies, for regular shaped bodies, the center of mass and center of gravity would be same. Okay, for regular shaped bodies, the center of mass and center of gravity would be just same, right? Because here also we want distribution of weights to be equal, right, to be symmetric. So is this point clear, everyone? Okay, all right. Then this is the center of gravity. Then let's talk about the lever. Okay, not L-I-V-E-R, L-E-V-E-R. Okay, lever. What is this thing? So what is lever? You might have seen, have you seen lever? All right. So see here, now this is our very basic lever. Okay, very basic lever. So here on one side we put some load. We want to lift that load. Okay, so suppose these are the weighing stones. Okay, or these are weights. Okay, weights which you get nowadays. You don't get that in grocery shops. Also they have electronic scales. Okay, so these are the weights. Suppose 1 kg weight, 2 kg weight, etc. You put that on this pan, sorry, in this pan, and this lever, okay, or this rod, it is pivoted about this point, and on the other side what do? You put weight, or let's say you put sugar, etc. Okay, so it can be anything in any pan. Suppose there is some sugar in this pan and you want to lift it. So what do? You put weights in the other pan, right? So the pan which you want to lift, okay, so this rod, this is the rod which is called as lever. So this side, this much length, it is known as load arm of the lever. Okay, the side that you want to lift, it is known as load arm, and the another side, okay, where you are going to put the weights to lift this, it is known as effort arm, because you are putting some efforts to lift this one, right? Either you can just pull this, okay, downwards, so that this part will be lifted. Okay, so you need to put some efforts, okay, physical efforts, or you put some weights over here, right? So suppose the load arm and the effort arm, the length of those two arms is equal, okay, as it is there in case of weighing scale, old scale weighing, okay, old school weighing scale. I am sure you might have seen it, at least in pictures, right? So in weighing scale, the load arm and the effort arm is equal, length of them is equal, right? If it is not equal, then what might happen? You will get lesser grocery, sometimes more, depending, right, depending on the length. Okay, so now what's the use of lever? Actually, this is a balanced lever. Okay, so what is the use of lever is, you want to lift huge weight using putting small efforts. Okay, you want to lift huge weight putting small effort, right? So see, this is the load arm, its length is L1. This is effort arm. Either you will pull it down, okay, in order to lift this case, this thing, or you will put some weights. Okay, so what do you want to achieve here is W2, that is the effort that you are putting, should be less than W1, right? So L1 is the length of the load arm, L2 is the length of the effort arm. So now what will happen? So suppose it is pivoted about this point, the lever is pivoted about this point, okay, then there would be torque due to these weights. Okay, so torque due to these weights. So see, if you see load arm, it's, I mean, if you draw the position vector of this force, it is directed like this. Okay, so this is L1, this is direction of L1, right? And this is the weight. So if you do R times F into sine theta, then it is trying to rotate the body in anti-clockwise sense. What's the body? The lever, in anti-clockwise sense. Okay, so it will fall down like this. Okay, so it wants to rotate the body in anti-clockwise sense. What about this weight? it wants to rotate the body in clockwise sense. Okay, if you do R cross F. So how much is the magnitude? So magnitude of the torque due to this one, due to this W1, it is just L1 times W1, because angle is 90 degrees, right? L1 is directed like this, W1 is directed like this. Angle between them is 90 degrees. So now this scale will be balanced, or lever will be balanced, when tau1 is equal to tau2. So tau1 is L1 times W1, tau2 is just L2 times W2. Okay, so now take ratio of W1 by W2, it is just equal to L2 is to L1. W1 divided by W2 is equal to L2 is to L1. Okay, so now see, if L2 is 100 times greater than L1, then 1 kg weight put in the right pan, it can lift 100 kg weight which is put in the left sided pan on the left hand side. This thing is clear? Yes, no? Because W1 by W2 is just equal to L2 is to L1, and this ratio of L2 is to L1, it is known as mechanical advantage of the lever. Okay, it is known as mechanical advantage of the lever. Okay, so is this point clear? How lever is used, right? So there was one physicist, I guess it was Aristotle, I don't remember clearly, but maybe Aristotle. He said, give me a lever long enough and I will lift the earth. Okay, so yeah, so this was the statement by, I guess, Aristotle. You can search that. Okay, so this is how lever works. Okay, so suppose you want to lift a heavy object, what will you do? Suppose you want to lift a heavy object, or you can take an example of seesaw. Seesaw is also an example of river. Okay, so here you have a man of 100 kg, right? It's a man or some machine, a truck, etc. So suppose there is a man of 100 kg on this side, and here is one child of 50 kg, or you can take 20 kg or something, right? So man sits on the seesaw, let's say at the middle of seesaw somewhere, okay, at length L1 from the point at which it is pivoted, right? Then what should be the distance at which this child sits so that the man is lifted, okay, or at least the seesaw is balanced? So what should you do? So W1 by W2 is L2 by L1, so that is equal to, W1 is M1G, W2 is M2G, GG gets cancelled, so M1 by M2 is L2 divided by L1. So L2 should be equal to what? M1 by M2, okay, times L1, right? And in this example, W1 is equal to what? 5 times of W2. So L2 must be equal to 5 times of L1, right? So if he sits at, let's say, 1 meter, then the boy should sit at the 5 meter, at distance of 5 meter. Okay, this thing's clear, everyone? Right? Okay, good. So now this is the end of theory of this chapter, at least, and there are some problems. Okay, so let's see this one. A couple produces, tell me, linear and rotational motion, no motion, purely linear motion, purely rotational motion. So option D, right? Yeah, good. So it produces purely rotational motion, Okay, good. Then let's see this one. A rod PQ of mass M and length L is hinged at the end P. So it is hinged at this end. This rod is hinged at this end, and the rod is kept horizontal by massless string. So this is a massless string, okay, tied to point Q as shown in the figure. When string is cut, you cut the string, then the initial angular acceleration of the rod is, what would be initial angular acceleration of this rod? This is the question. Tell me. So see, this is simple question. Now when string is cut, what will happen? So suppose this is the rod, it is hinged at this point, and it was suspended by means of a string on the other end, right? It was suspended like this. When string is cut, what happens? It will fall down like this, right? It will fall down from the, right, it will fall like this from the point, okay. It will rotate about a point where it is hinged, right? So this thing will rotate about point P, okay. So is this thing clear? It will rotate, this rod will rotate about an axis passing through point P. So therefore now what we must do is we should find out torque due to whatever forces are there about point P, right, about point P. So when you cut the string, there is only one force left. What force is that? It's the gravitational force, okay, and it will act at the midpoint, right? So the force is equal to mg, and it will act at midpoint, that is at length L by 2. So what is the torque? Therefore the torque is equal to R into F multiplied by sine theta, okay, but it is R and F, they are directed at an angle of 90 degree, means sine 90 is 1, so it is just R times F. So what is R? R is L by 2. What is F? F is the gravitational force. So therefore this torque is equal to L by 2 times mg. And what is torque? You want acceleration? No, you want angular acceleration, right? Initial angular acceleration. So initial torque is this much, initial angular acceleration you want to find. So you write torque is equal to what? I times alpha, right? You know this formula, torque is equal to I times alpha, and therefore what will be alpha? Alpha is, take I on that side, okay, so I goes in denominator, okay, so alpha is L by 2 mg divided by I. It's very, very simple, right? So L by 2 mg, m is m, okay, g is g, and then what is the moment of inertia of this rod? This is the question, okay. What is moment of inertia of this rod about a point or about an axis? So option C, let's check. About an axis which passes through one of its edge, okay. We don't want moment of inertia about midpoint. ml square divided by 3, right? ml square divided by 3, good. So it is ml square divided by 3, okay. So m and m gets cancelled, then this L gets cancelled with the square, take 3 in the numerator, so it's 3 by 2 g divided by L. That's the answer. So alpha is equal to 3 by 2 g divided by L. So it is option C. So Bhanu said option C, right? Very good. So this is simple. Yes, no? Okay, good. Then let's see next one. Let's see couple of problems. Okay, this one. So a uniform rod AB of length L and mass m is free to rotate about point A. The rod is released from rest in horizontal position. Given that the moment of inertia of the rod is ml square divided by 3, they made it simpler. This came later, right? This was earlier. So this is the same problem. The initial angular acceleration of the rod will be, repeated thrice at least. Okay, 2006, 2007. How can they repeat? I don't know. In the interval of 1 year. Okay, 2006, 2007, and 2013. Right? So answer is 3G by 2L. Same question. Okay, it's the same question. Let's see next one. Let us see couple of or at least one question. Okay, then we can call it in, right? Because we can't keep 1 or 2 questions for the next time. Okay, so let's see this one. A uniform horizontal meter scale of mass m is suspended by 2 vertical strings attached to its ends. Okay, so you have a scale, you have uniform horizontal scale, oh, uniform horizontal scale like this, and it is suspended by means of 2 vertical strings attached to its 2 ends, right? 2 vertical strings attached to 2 ends like this. Okay, and then a body of mass 2m, the mass of scale is m, so mass of scale, now it will act downwards from the midpoint, right, from the center of mass, so it is mg, right? A body of mass 2m is placed on 75 centimeter mark, so at 75 centimeter mark you put body of mass 2m. Okay, so this is at 75 centimeters, right? So its weight would be equal to 2m multiplied by g. Okay, 2m times g. Then the tensions in the 2 strings are in the ratio. Okay, tension in this string as well as this string, they are in the ratio. This is the question. Okay, so see, in this kind of question we need to consider both equilibriums. Okay, so which 2 equilibriums? One is the rotational equilibrium and one is the translational equilibrium. So first let's take translational equilibrium. So for the translational equilibrium, these two forces T1 plus T2 are acting upwards. They must be equal to the force that is acting downwards. So that is mg, okay, weight of this one, weight of the scale plus weight of this weight, 2 mg, right? Mg plus 2 mg is 3 mg. So you got T1 plus T2 is equal to 3 mg, right? So let's call this equation 1. So because you want to compare them, okay, T1 and T2, either you need to find them or you need to compare them. So 2 unknowns means you will need 2 equations. So one you got from translational equilibrium, okay. Now for rotational equilibrium, the torque, net torque about any point must be equal to 0, right? So let's call this as point A, this one is point B. So net torque about any point must be equal to 0. Okay, so let's take torque about A. Let's take torque about A. Let's take torque about point A. Okay, so this first force, that is T1, tension in the string, it passes through A only, therefore there is no torque because of that. Okay, then this m1g is at distance of L by 2, right? How much is this distance? L by 2, this is 50 centimeters. Okay, this is meter scale, right? So this is 50 centimeters and this is at 75 centimeters, means this is at 3L by 4, right? The second weight is at 3L by 4, and this one T2, it is acting in the opposite direction, it is acting upwards, it is at distance of L, right? So let's write down the torques. So let's suppose clockwise are positive, anti-clockwise are negative. Okay, so this one rotates the body in clockwise direction. So let's suppose this torque is positive. So you have L by 2 multiplied by mg. This is positive. Then in what direction is this weight rotating the body? In the same direction, right? Okay. Yes, no? Suppose axis of rotation passes through point A. Okay. It is perpendicular to length of this rod. So then this weight, it will rotate the rod in clockwise sense. This weight will also rotate the rod in clockwise sense only. Yes, no? Because they are on the same side. Okay. And they are acting in the same direction. So this is also positive. So plus, how much is distance of this one? It is 3L by 4. Okay. So you have 3L by 4 multiplied by 2 mg. 3L by 4 multiplied by 2 mg. Then now this tension is acting in upwards direction. So these weights, they try to rotate the rod in this direction in clockwise sense. Tension wants to rotate the rod in anti-clockwise sense. So you should take minus of L multiplied by T2, and this all must be equal to 0. Okay, this all must be equal to 0. And from this one we can find out T2. Right? So is the equation clear? Is the equation clear? This one? Right? Then now what I can do is I can say I can cancel out L everywhere, and then I have mg divided by 2 plus 3/4 of 2 mg, so that is 3 mg divided by 2, right? 3/4 of 2 mg means 2 by 4 is 1 by 2. Okay, 3 by 2 times mg, it's equal to, take T2 on other side, so it's equal to T2. So mg by 2, so this is half mg plus this is 1.5 mg, so this is 2 mg. So T2 is equal to 2 mg. You got this, and you have equation 1, T1 plus T2 is 3 mg. So from equation 1, I have T1 must be equal to what? Mg. And therefore they asked about the ratio, therefore T1 is to T2 must be equal to what? 1 is to 2, because T1 is mg, T2 is 2 mg. Right? This thing is clear? Everyone? Okay. So this is how we can solve the problems based upon torque and rotational equilibrium. Right? So we took 2-3 problems, and problems would be similar. Okay, so try to solve homework problems. Right? If you get them, that's well and good. If you don't get them, you can ask me. Okay, so we'll call this as end of this chapter.